Hey, wait, wait.
Solid C. Yeah. You know, initial spell it down. Billion, Alonzo. We look on fire. There. What? How do you say it? Is that right? You have a business again. Maybe the whole injury, I don't know. Business. So that's why he jump. That jump. It's working. I gone. That's how we have. The hospital side. You have an undercut teaching me? I don't know. I'll be realize what you man, let that person do people get show. You gotta open what happens. You need to have to do the task. Yeah, don't want to do tasks. Because you feel like it's how was it? It's a really, I thought it was fine. Of that. Yeah, for this stuff? Yeah. It's nice, I enjoyed it. I'll show you, it wasn't bad. Do you read those? Professor, I'm gonna keep it. Do you read the assignments?
What assignments?
Like the one that we do?
Oh yeah, of course. Read all of them.
I was just saying, like, do you learn new stuff because of like people doing research on it?
Yeah. I don't have time to keep pace with like all the new advances with technology nowadays. And so when I do these things and you guys do your research, usually you guys are looking up articles that are more recent that I haven't taken a look at yet. And so it gives me a chance to kind of learn from that too. Yeah.
Because I mean, it's say, yeah. I know, I feel. My friend's brother, and then it's a person.
Well, I have to be careful because I was just saying some of the stuff that I learned from Edwards. Well, none of it's sophisticated. They have their traditional Bible files and they're able to insert the paper valve into it. So that'll be effective. It's in your hole, you know.
Get yourself to that. Yep, you're still up, you know, yeah. Yeah. Basically shot.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today?
Good.
Good. Everyone have a good weekend? Anyone watch Super Bowl?
Yeah.
Oh, a lot of Niners fans here, I see. Yeah, I had a lot of friends over my place to watch the Super Bowl. Although my friends, they're not too interested in football. The ones that are the ones that like to do sports betting. So I had a lot of people that were actually pretty unhappy leaving my house. But seeing Usher at the halftime show was great. I grew up listening to Usher, so to see him perform was amazing. So I think that was my favorite part of the day. All right. So today, we have a little bit of a fun day today. So, this whole week is kind of centered around Synvascular. So I think on Friday, I sent you guys an email to download the software. So we're not using the software today, but we are going to do our workshop on Thursday. So to prepare ourselves a little bit, I have a little bit of a primer today on just medical imaging in general. And so we'll talk about what that means. The different forms of medical imaging, the different types of information that you can get from it, because that's a big part of Synvascular. And so it's important to kind of know kind of the origins of how the CT scan was obtained and what exactly is in it and how they got that. That's important for Thursday. And then, of course, Thursday, that's when we're going to run our workshop. Okay. So a little bit about Vascular. So it is very much a research software. It's different in nature to, I think, probably a lot of the softwares you've used in your other classes, which are more commercial softwares. So softwares like SolidWorks, MATLAB, ANSYS. I think you guys are also running CATIA as well if you're in 422. Those are softwares that are more designed for commercial use, for companies to use. So they're a lot more polished. They have full development teams behind it. They're designed to make money. So what you'll learn very quickly is that a research software is quite different than that. It's the research softwares are usually have a much smaller development team. And most likely they're very underpaid and very hungry. So there's going to be some errors associated. The software may crash on you. So I'm just giving you a warning right now. But being a research software also means we can't install it on the school computers here. And so you guys have to install it on your own personal laptops. And so I haven't had too many issues with it in the past, although a couple students have had issues installing the software. So I don't want you guys going out and buying a new laptop if it doesn't work well on your system. If it's not working out well, then let me know. Then we can work something out for the project. Okay. But please don't go out and buy like a $700 laptop just for this class. It's not worth it for that. But that's the reason I'm having you guys all download and install it, because we just because of the IT limitations here, we're not able to install it here on these computers. Okay. Yeah.
Is Apple or
Apple works, yes. And so it's actually a nice thing. So it actually works on Windows, Mac, and Linux as well. And so if you on the weird off chance you have a Linux machine, it works on that too. Okay. All right. So I don't have the next homework ready yet for you guys, and so I want to kind of proceed a little bit with the lecture notes before we do that. So probably next week is when we'll have that. But because we're doing our first vascular workshop this week, I do want to introduce the project. So we'll probably talk about that either Thursday if we have time, or early next week. So I want you guys to kind of start thinking about the project and possibly start working on it soon too. So that's why I'm kind of delaying a little bit posting the next one. All right, any questions I can answer before we get started for today? Okay. All right, so let's go and get started. So I have these lecture slides here on medical images. I don't think it's going to take the whole time, so I did bring some more lecture notes just to fill the rest of the time, but we'll see. If it does take the whole time, then that's fine as well. All right, so here are the objectives, and so we're going to define medical imaging. Some of these terms you may be familiar with, like X-rays, MRIs, but we'll talk about those a bit more. And I think more importantly, we'll talk about kind of how these are done and how they can help us with computational modeling. Okay. So what do I mean by medical imaging? So medical imaging is kind of a broad term that's used, clinically to refer to any kind of diagnostic equipment that's meant to give you visual information, usually inside a patient, right? And so it's usually some kind of imaging that's done to view the internal organs or bones or blood vessels inside a person that you can't normally see from the outside, right? And so some examples that you may be familiar with that you've probably gotten at some point in your life are things like X-rays, MRIs, ultrasounds. So they all kind of fit under this umbrella of medical imaging, okay? So typically, medical imaging, they're used by medical doctors, and they're used to assess the health of a patient, diagnose disease, or even for research. So you've probably, everyone's probably had an X-ray done on them at some point. Maybe you hurt yourself, playing sports or something, and they had to take an X-ray to see if your bone was broken. If you've been to the dentist growing up, they probably took X-rays of your teeth to see if there's any cavities in there. So it's very often performed. It's almost, I would say, pretty much a part of regular kind of medical practice nowadays, right? So today, we're going to go over the different types of imaging techniques. We'll explain a little bit about their physics. You'll see that there's actually a lot of really interesting physics behind a lot of these technologies. And most importantly, we're going to discuss applications, which is kind of what we're mostly doing. Okay. And even though medical imaging, it exists for a wide range of the different biological systems inside the human body, just by the nature of this course, we're going to focus mostly on cardiovascular imaging. So anything that has to do with the heart and your blood vessels. Okay, so let's talk about the types of medical imaging that's available. And so there are two main categories of medical imaging that's done. in a clinic. And so the first is called structural imaging. So this is probably the type of imaging that people have had done before. So this is pretty kind of standard of care. And so this is mostly to provide information on the geometry and the motion of any kind of internal organs or blood vessels or bones of a person's body. So it's strictly just an image. It's just a picture and nothing more, right? And so the idea behind structural imaging is to give you a visualization of the organ shapes, the volumes, blood flow patterns, and speeds. Okay. So the most common types of imaging techniques that you'll find in this category are things like X-rays and MRIs, which we'll talk about in detail. Right. The second type of imaging, which is usually pretty rare for young healthy individuals, but becomes more common as people get older and start to develop health problems, is a category called functional imaging. And so not only does functional imaging provide visual detail of kind of the size and the shape of your internal organs, but also provides some information about function as well. And so this usually is due to just kind of some other test that's done alongside the imaging. And so one common example of this is something called blood perfusion testing. And so in this particular type of imaging, a dye is injected inside a person's body, and then an X-ray is basically used to track how that dye perfuses into a muscle or perfuses into an organ. Because it could happen. One common thing that can happen in older people is that maybe their larger blood vessels are performing just fine, but the blood is actually having a hard time penetrating and perfusing into the muscles, into the organs. And so using an imaging type like this, doctors can more easily see if there are particular organs that are not perfusing the blood or perfusing the organs that well. Okay. And that could suggest things that maybe they need a replacement kidney, or maybe they need a replacement organ or something like that. Or maybe they can target particular areas for operation. Okay. And the injection, what doctors usually inject is often called a contrast agent. And so it's usually some kind of inert chemical, something that causes no harm to the human body, and just honestly, you just pee it out eventually. But it's made of a certain material that when you X-ray it, it actually shows up very bright. Because the common challenge that you have with medical images is that a lot of the parts of your body, honestly, your body's made up of a lot of water, and so if you run an X-ray through it, a lot of your blood vessels and a lot of your organs are not really going to show up in the image. The only thing that really shows up are your bones. And so in order to get things to stand out more, and a contrast agent is actually injected to make sure that they show up nicely on the images. And that's common also as well in structural imaging, but it's almost a requirement for any kind of functional imaging out there. Okay. So here I have a couple images for you. So on the top here, this is a CT scan of someone's brain. It's a beautiful image, and so usually you don't get images with very clear kind of. You can even see the folds of the brain, which is kind of crazy. And you can see the nasal cavity and the mouth and kind of the esophagus and things like that. And you can even see the brainstem. So this is a particularly kind of beautiful image of the brain. But again, it's just an image. So this would fall under structural imaging, right? Down here, what I don't remember the exact context of this, but then you can see that certain areas are kind of lighting up on the image, and this is probably due to some kind of contrast agent kind of perfusing this area and showing kind of function. Question? Yeah.
Will the CT scan be under?
Yes. Mostly CT scans are functional images. Yeah, we'll talk about CT scans a lot more. Question?
Yeah. You know how they go about it? It seems like it's like perfectly bisected at first. Like, how does it go through one side of someone's head and only sees the other side? You know what I mean?
Yeah, no, that's a great question. It's a question of kind of the geometry. And so you'll see in a bit when an X-ray, the way an X-ray works, that you kind of shoot the X-rays kind of through a person, and it's collected onto like basically an image on the back. And so based on kind of how close you start that X-ray tube and how far back it is, there's kind of an optimal place where kind of it's called attenuation, where like the X-rays are kind of attenuated at a certain point, and then you can kind of adjust to see kind of which plane that you want to see most.
So it won't go like so far, essentially.
Exactly. Yeah. Mm-hmm. Yeah.
X-ray need to like be.
Yeah, actually, so I don't know exactly how they got this, because usually you want to avoid sending radioactive stuff through your head. It's usually not a good thing. So yeah, yeah. So I think that's what this makes this image even more remarkable, that they were able to get such a beautiful image. Because usually, yeah, you want to be really careful about radioactive rays, going through a person's head, because that's what causes mutations and stuff, and you don't want that to happen in the brain for sure. Yeah. All right, any other questions on this slide here? Okay. Okay, so let's talk about X-rays. So X-rays have been around basically for forever, and so it's one of the oldest forms of medical imaging. It dates all the way even back to the 1800s, which is crazy. So the way it works, or kind of the basics of how it works, is that X-rays, which are a type of radiation, are produced in a device called an X-ray tube, and then literally kind of shot through the patient. And then on the other side, you have another device called an X-ray detector, which kind of collects those X-rays and forms the image. And so the different bones and tissue inside a person's body will attenuate the X-ray beams differently. And so what attenuation basically means that the higher degree of attenuation means that it blocks the X-rays. And so the reason X-rays are so effective at seeing bones is that bones are full of calcium, and calcium is basically a really strong blocker of X-rays. And so actually what you see, so when you shoot the X-rays through a person's body, your bones actually stop a lot of the X-rays. And what you're seeing here is kind of the negative, almost kind of like the negative space, of the X-rays that didn't make it past the person's body. Right? So out of all the materials that are commonly inside a person's body, calcium is probably the strongest attenuator. And so when people think of X-rays, they think of seeing the bones inside your body. So that's probably why it's most effective in doing that. So a lot of the soft tissue inside your body, your muscles, your blood vessels, your organs, they do attenuate the X-ray beams, but often very lightly. And so you can see a little bit here. So kind of in between, this is kind of the space in between the person's thumb and their forefinger. You can see that it lights up a little bit because it's probably some fat that this person has in here that's kind of blocking the X-ray a little bit, but it doesn't show up nearly as bright as the bone because the fat's just not as effective at blocking X-rays. And so when you're using X-rays to image the cardiovascular system, this actually presents a big issue because blood has a lot of very similar properties as water. And so blood by itself is not going to attenuate the X-rays. And so, you can see in this image right here, even though this is the person's hand, there's actually blood vessels that are going all throughout this person's hand, right? But we don't see any of that because the blood doesn't attenuate the X-rays on its own. And so if you want to see a person's blood vessels or their heart using an X-ray, you almost always need to inject a contrast agent inside a person's body in order for that to show up. And so the most common one for the cardiovascular system is iodine. So iodine, it's not pure iodine, that would be poison, but it's iodine kind of mixed with water. In the kind of the perfect amount that's not enough to poison you, but enough to show up on the X-ray. And then if you want to view your gastrointestinal system, so things like your lower intestines, your stomach, things like that, they often have people eat barium, and then as that kind of flushes through the system, they can get a nice image of your lower intestine, your upper intestine, things like that. Okay. All right. Any questions on X-rays here? Of course, ever since then, X-ray technology has come a long way. And if I've had the privilege to actually go to a conference or two for people that work on this technology. And ever since it was developed, there's always a concern about radiation because X-rays, if you're exposed to X-rays for long enough, then it can cause mutations of the cells in your body, which is very bad because that leads to things like cancer and things like that. And so there's always a concern. There's always kind of a lever that people are modifying because usually the more radiation that you give, the more beautiful images that you get, and the less radiation that you give, the patient's generally safer. But then if you don't give enough radiation to actually see the problem that you're looking to define, then you kind of just expose your patient to radiation for nothing. And so it's a very fine balance in terms of how much radiation do you give. And honestly, you know, talking to a lot of radiologists, it's not really an exact science. And so there's a lot of intuition that goes with it in terms of, you know, how the patient is, what condition that they may be having. And so, you know, there's definitely a lot of room for improvement in that sense. Okay. So next, let's talk about kind of the step up from X-rays, which is the CT scan. So CT stands for computed tomography, and so this is a quite a modern imaging technique, very common nowadays too. And so CTs are actually kind of just a step up from X-rays, and so it's kind of like X-rays but 3 dimensions. Because the thing about X-rays and the way that they're designed, they only really produce a 2-dimensional image of whatever you're trying to image, just because the X-ray only goes one direction and you collect literally just like a snapshot from behind. But you know, a lot of the organs and a lot of the you know, things that you want to image inside a person's body are 3-dimensional, right? Your heart has a 3-dimensional shape, your blood vessels go in 3 dimensions, right? And so if you want a proper kind of, you know, picture of how those things, of their shape, of their volume, their direction, you need a 3-dimensional image. And so CT was developed with that kind of goal in mind, is that how do we use this X-ray technology and how do we produce a 3-dimensional image from it? Okay. So you've probably more than likely seen a machine, something like this. You know, you've either maybe have been inside one of these machines, or maybe you've seen them in like a TV show or something like that. But this is essentially how the CT scan works. And so what you don't see is that inside this ring right here is actually this. So the way a CT scan works is that it's essentially the same as an X-ray, except that the X-ray, let me kind of draw it in here so you can see. So, you know, the X-ray tube, you know, might be something like this. And then on the other side, you have the X-ray detector right here, right? This is a very crude image, right? And then as a patient kind of goes inside here, both of these things are going to rotate in a circle around the patient, okay? And then while it's rotating, you know, it's actually shooting X-rays all throughout. And so you're basically gathering tons and tons of images from many different angles around the patient. And then from there, you know, you have all these images from different angles. And so you have an X-ray that's like this, going through a person's body, one like this, one like this, one like this, one like this, right? You have all these different images. They're all kind of, you know, imaging the same patient. They're all just kind of pictures taken from different angles. So from here, you know, there's actually a lot of kind of computer processing that has to go through a technique called back projection. Okay. And through back projection basically takes all these different slices, different angles, and kind of collates them into a nice orderly stack. And so instead of getting images from all these different angles, what you get instead is kind of like a stack of images that you kind of see right here. Okay. So it's literally almost like a stack of papers. And so, you know, as you know, right here, you can see kind of a 2-dimensional shape here. And then that 2-dimensional shape is kind of stacked on top of another one, right? And then eventually you kind of have a 3-dimensional box of of an image of a person's organs that's been developed through the CT scan. Okay. So it's actually a very fascinating technology and a lot more engineering than I thought when I first kind of learned how this works. And of course, you know, this is just a very short introduction to how it works, but this is kind of how, you know, doctors have kind of solved this issue of you know, producing 3-dimensional images using a 2-dimensional technique like X-rays. Okay. All right. So CT scans are going to be really important for this class, because that's going to be the main imaging modality. Because, you know, if you're going to be viewing the cardiovascular system, like blood vessels in the heart, CT produces the most consistent, high quality images that we can get. And so, you know, for almost everyone, I think the vast majority of the projects that I have, or the image set that I have, are CT. I think I may have 1 or 2 MRIs, but I think for the most part, they're all CT scans. So when we do our tutorial on Thursday, we'll be working with a CT scan of a real person's body. And you'll see that it kind of has this kind of stack organization. So kind of thinking of the CT scans of like stacks of 2D images, one on top of the other. I think that kind of intuition will really help you as you're learning how to use Vascular. Okay. All right, questions on CT scans? Okay, so next let's talk about the next most common imaging modality for producing images of a person's organs, which is MRI. So MRI, if you follow sports in any capacity, MRI is a term that's thrown around a lot. And what it stands for is magnetic resonance imaging. Okay. I remember the first time someone explained MRI to me. The first thing that they told me is that MRI, like whoever discovered MRI and figured out the way this works, like they must have like seen Jesus or something, because there's no other way to explain how someone could come up with this. And as I kind of learned more and more about how the techniques works, and it's like, yeah, this person met Jesus. There's no other way they could have figured this out. So MRI, just like the name implies, really heavily involves using magnets to produce images. And the way it works is that it kind of works by affecting the polarity and affecting the spin of the atoms and molecules inside a person's body. And so the way it works is this. And so, as everyone knows, the different types of atoms for the different materials all have different numbers of protons and neutrons and electrons inside of them, right? That's part of what makes them different elements in the world. Okay. So hydrogen atoms, which make up about 62% of the mass of a person's body, because they only have one proton and one electron, and sometimes less than that, they are very highly susceptible to being magnetized. And so if you expose the hydrogen atoms inside a person's body to an external magnetic field, it's going to affect their spin in a particular way, right? And so in particular, if you expose hydrogen atoms to a 1.5 Tesla magnetic field, they'll spin with a frequency of 64 megahertz. And then if you expose them to a magnetic field of 3 Tesla, they spin with a magnitude of 128 megahertz, and then everything in between as well, right? These frequencies, just by pure coincidence, also happen to be the same frequency as radio frequency, right? So the exact same type of technology that you use to pick up radio signals in your car, these hydrogen atoms kind of spin with that same frequency. So you can use kind of that same technology to kind of pick up this spin. And so the way MRI works is that first you have a giant magnet around a person, and it first generates this magnetic field to align kind of the spin of these hydrogen atoms in a particular way, right? Then what happens is that you have an RF transmitter. So RF stands for radio frequency, basically tilts the magnetic field in certain ways so that you can kind of produce an image from it. And then based on how you manipulate these tilts, only certain atoms are affected, depending on the amplitude and the duration of the transmitted signal. And this is kind of further complicated by the fact that, if you turn the signal off, the atoms can actually relax to kind of their natural state as well, which you can also pick up. You can kind of pick up that kind of relaxation state. And so this is a lot of mumbo jumbo, and honestly, I wish I knew more about this. MRI was something I studied very intensely for about a month when I was in grad school, just out of pure curiosity. And I still feel like I don't fully kind of understand how it really works. But MRIs, actually, interestingly enough, are still also a very hot topic of research, because the particular sequence in which you kind of pulse the magnetic field, how you turn it on, you turn it off, how you tilt it, how you change its directions, different sequences actually produce different images. And so what you can see right here, what I'm showing you here is an MRI of a person's chest cavity. But you can see that they look slightly different. So one's brighter than the other one, whereas one is kind of picking up more of these kind of, this looks like the lungs. I think this is the lungs, because inside the lungs you have a lot of these kind of little, kind of almost like fractal fragments that you can see, which are all kind of the channels that your body uses to take in oxygen. And so in one image, you can see them a lot brighter than the other one. That's because these were produced with different RF signals or different MRI sequences, right? And the manner in which you can develop these sequences is actually still, there's honestly, an infinite amount of possibilities for sequences. And so, there's literally, radiology people researching radiology that are just trying different MRI sequences and seeing kind of what works out, and then kind of studying and analyzing why this particular sequence worked out. So, there's still a lot to be learned with MRI for sure. Okay. So MRI it's not as common for viewing cardiovascular stuff because the thing about MRI is that it's a lot slower than a CT scan. And so if you're viewing kind of your cardiovascular system, which is, has a lot of motion, has a lot of pulsatility, it's not the best at kind of picking that up. And so MRI is kind of more, it's more common for viewing kind of structural tissue, so things like ligaments and tendons. So that's why you kind of see it heard, you kind of hear it more talked about in the sports setting for, if someone sprains their ankle or someone sprains their knee, usually they get an MRI to see kind of how their tissue is. But there are still some applications with MRI. And in fact, there's one particular application called PC MRI, phase contrast MRI, which does have an advantage over CT. But PC MRI is also very difficult to do. Okay. All right. Any questions on MRI? Yeah.
Well, I know like X-rays, you're getting blessed with radiation. Is there like a, that's why not, but is there like a magnetic field that's dangerous? Is there like a certain level of magnetic field that could be dangerous?
Not to the same sense as radiations. So there's no risk of kind of cell mutation. And there's no studied risk of like messing up anything inside your body when exposed to a magnetic field, because there's nothing metallic inside your body. So nothing can really be displaced. Now, if you are getting an MRI, you have to make sure you're very honest with your doctor. And so if you have any kind of metal teeth or any kind of pacemaker inside your body, you need to tell your doctor that, because if you go into an MRI with those metal things, you will certainly die if that's the case. But usually that's communicated very clearly to patients. And so that was only really an issue kind of very early on. So yeah. Question?
What was the PC MRI? How does that differ from the?
Yeah. So PC MRI, that stands for phase contrast MRI. And so phase contrast MRI uses a very particular sequence for the RF signal. And then from that, you can actually view the blood velocity, which is something that you can't get from CT scans. So CT scans is strictly a structural imaging modality. So you only see just the geometry of the blood vessels, but it doesn't tell you kind of the speed of the blood flow. And so I know PC MRI is used a lot inside the heart, actually. And so if someone has a faulty valve and you want to see kind of backflow out through the valve, PC MRI is used often, because then with PC MRI, you can actually see the blood flow coming back out through the valve.
Is it the same where it's going to be like a stack of images, or is it?
So with PC MRI, you mostly see the motion in just one slice. You do get a full stack slice of the entire geometry, but the place where you actually see the phase contrast is just one slice. Yeah. Any other questions on MRI? I had an MRI done on me before. So it was in my first quarter as a grad student. And one of my lab mates is like, do you want an MRI? Like I need some data for my research. I'm like, yeah, sure. I'm like, yeah, sure. I never had an MRI. He had me sit inside an MRI tube for 4 hours while he kind of like spun the thing around me. And like when you're inside, if you've ever been inside an MRI machine, it's very cramped. So you're laying down flat and literally the thing is right in front of you. So you can't move. And so all I hear from because he had me wear a headset so I could hear him, and he's like, "You're doing great." I'm like, "I'm hungry, man. Get me out of here." 4 hours. It was a long time. I knew no better, but then since then I knew better not to.
Is that the average time?
No. He wasn't messing with me, but he wanted to run. He was basically testing different sequences, and so he was trying out a lot of different ones, and he couldn't get someone to sit inside a machine for 4 hours, except for the bright-eyed freshman that just joined the lab. So that's never again. That was my last time inside an MRI machine. Yeah, it's interesting too, because it actually gets pretty hot in there too, because it takes a lot of power to generate the magnetic field, and that heat has to go somewhere. So it almost kind of feels like you're inside an oven a little bit. So I was sweating a lot inside that machine. It was not a great experience, that's for sure. Okay. Next form of imaging, not as common for what we do, but it does belong in the same family. So it's so I should mention it is ultrasound. So ultrasound is a very interesting technique, because it's physically it works on very different principles than like X-rays or MRIs, because ultrasound relies on sound. And so the way it works is that, you know, it's if you've ever had it done to you, or you've seen it done, you'll see that there's like almost like a magic wand that the doctor uses, and they kind of push it onto your body, and then kind of use that to generate an image. And so what that wand does is that it produces a very high frequency sound, usually on the order of 2 to 20 megahertz, passing through the patient, and then seeing how those sounds actually reflect back. And so the thing with sound waves is that, you know, as sound kind of passes through different medium, whether it be air or water or tissue, you know, the speed of sound is affected by it. And when sound waves kind of reach kind of a relatively solid object, you know, those sound waves are scattered and reflected back. And so, you know, based on the character and based on the amount of sound waves that bounce back to the transducer, you can kind of process this, you know, in a computer to produce an image, which is what you see kind of right here, right? So I think most commonly ultrasounds are used for, you know, for fertility, for viewing babies inside, you know, pregnant mothers, right? But it also has some applications for cardiovascular as well. So one actually really interesting application is using the Doppler effect. So did you guys learn about the Doppler effect in your physics class at some point? And so the Doppler effect, the way it works is that, you know, the sound that you perceive, you know, depends on your velocity, basically. So I think the example that everyone uses is that, you know, if you're kind of standing on the sidewalk and there's a police car or there's a fire truck that's kind of has their sirens on, running towards you, right? The sound of the sirens that you perceive, you know, change as the fire truck is coming towards you, and then as the fire truck gets away from you, because that velocity actually affects, you know, the frequency that you perceive here, right? And so ultrasound kind of works in the same way. And so if you take an ultrasound transducer and you actually shine it kind of directly down the barrel of a blood vessel, you can actually make use of the Doppler effect, because as those sound waves kind of reflect off of the moving blood, you know, it's going to be affected by the velocity of that blood as well. And so the character of the image that you get is going to be dependent on that velocity. And so this is often used kind of in the same context as PCMRI, to kind of view flows inside the heart. So I will say that it is very difficult. And actually, if you're going to use ultrasound to view blood flows, you need a very skilled operator to do so, because the heart is something that's kind of constantly moving, and finding the exact right angles to give you good data is really difficult. And so not everyone can do this. And in fact, you know, the ones that can do this are the ones that are very highly paid by the hospital. So that this is not easy to produce. But if you're skilled enough, what you can get is you can actually get some images of, you know, blood velocity. And so what you're seeing here is an image of inside a person's heart. So this looks like the left ventricle and the left atrium, where you can actually see the velocity of the blood passing through the ventricle. And this was produced purely from ultrasound. So this is very attractive from a lot of practicality standpoints, just because, you know, ultrasound, it doesn't require any kind of injections. It doesn't require any kind of big machinery. It's very cheap. And so it's very good if you have a person that's skilled enough to use it. That said, the image quality that you get is usually very poor. You can see here there's a lot of static. It's a very grainy type of image. And this is one that's particularly kind of beautiful too. So ultrasound has very limited uses. I would say it doesn't have a lot of applications yet for engineering or computational modeling, just because the quality of the image is so poor. So this is kind of more used clinically as kind of like a qualitative tool for doctors to diagnose things like valve failure and things like that. But it is an interesting topic, and I think, you know, I think there's some potential there for someone to come in and really improve it, you know, with maybe a more accurate transducer or something like that. Okay. All right, any questions on ultrasound? Okay. So those are the main techniques that are most relevant for the cardiovascular system, at least the ones that are non-invasive. And so there's a few more techniques here. So this table I found has things called SPECT and PET scans. You may have heard of PET scans before. These are not as common nowadays, at least not on the West Coast for hospitals here. You may see some hospitals, you know, in other parts of the country or other parts of the world that use these, but these are kind of a lot less common, mostly because of the cost. and kind of what you get from these. And so, you can see here that the CT scan is very reasonable. I mean, $200,000. I mean, that's still more reasonable than 1.2 million. So that's why you see CT scans are kind of more common nowadays, just because it has a good cost ratio. But these types of scanners do exist. They're just not as common nowadays. And so here are kind of the stats of each one. And so besides the cost, I think that's probably the line that kind of jumps out to everyone. But the one that's probably going to be most relevant for us is the spatial resolution. Okay, so spatial resolution basically tells you the quality of the image that gets produced through this technique. And so the smaller these numbers are, the more fine your image is going to be. So the higher quality the image. And so for cardiovascular applications, CT is going to be the most common for us, just because the cost, right? And so a lot of hospitals can buy one of these, and it's not going to break their bank. But it also gives you some really good spatial resolution as well. And so you can see here that it's you get almost 0.5 millimeters of resolution, really good. Whereas even for MRIs, even the best MRI machines, you're getting maybe about 1 millimeters of resolution, which is almost twice as worse as CT. And then here's kind of the other thing that kind of stands out too, is the acquisition time. And so you can see a CT scan only takes a few seconds. And so just, you go, if you've ever had a CT scan, it's actually quite quick. You just they wheel you into the machine, you kind of hear it going, kind of spins around for a few seconds, and then you're done. Whereas for an MRI, it can take 15 to 20 minutes or 4 hours sometimes, depending on if your friend's doing it or not. So, so MRIs take a lot longer to do. So, there's a lot of really interesting information on this table, and honestly, some of it might be a little bit outdated, because you can see here that this is for 2015. Probably these are a lot more expensive nowadays, but probably the same trends are still there. I don't think there's been any kind of huge breakthroughs in MRI science to make this any cheaper. So everything is kind of relatively roughly the same price. Okay. So that's it for the non-invasive techniques. And so, everything that we've covered so far, I would kind of classify as non-invasive. So they don't, besides, with the exception of maybe kind of a small injection of like iodine into someone's body, there's nothing that's kind of, nothing invasive into your body. All the machinery is kind of on the outside. With that said, there are a lot of imaging techniques that are invasive. And so these often involve, sticking a probe inside a person's body. And so the one I think that comes to mind first when people think of this are catheters. So catheters are these kind of wire-like probes that are literally kind of stuck inside a person's body, and usually these are stuck just due to the logistics and kind of ease of access. These are usually stuck in places that are not comfortable for the person, and so in particular, if you want a catheter to go to the heart, the easiest route or the fastest route to access this is to actually stick the catheter up your groin. Not actually up your anus or anything like that, but in that area. So you have kind of doctors kind of like this in that area, which is not comfortable at all. And so but the way a catheter works is that it's this kind of wire-like probe, and then they kind of stick it in through your groin and kind of snake this probe through your blood vessels over to the area of interest, which most of the times is going to be around your heart. And then once they have the catheter inside your body, they can actually put different types of instruments at the end of this wire. And so you can see here that there, as part of a catheter, there's something called a guide wire, which is kind of this blue kind of tipped object right here. And so it's mostly hollow. And so the first step in any kind of catheter kind of operation is to kind of get the guide wire into the place where it needs to be, whether it be near your heart or your certain blood vessel. And then inside that wire, they'll kind of snake different probes, whether it be a pressure probe or a flow probe, or they can even deploy some kind of medical devices from here as well. And so I think some of you probably studied this device called a stent. And so a stent is an object that doctors can use to kind of literally kind of open up a blood vessel. It's like almost like a wire mesh that they go in and they kind of expand it and kind of push out all the plaque out of the way. And usually that's deployed on a catheter like this. Yeah. And then I think another device that probably you guys learned about was an aneurysm coil. And so those are kind of metallic coils that are put inside a person's body to kind of gum up an aneurysm, those are also deployed through a catheter as well. So catheters, you know, there's been a lot of developments on these. There's been a lot of really interesting developments. It's just not a comfortable procedure to do, just because it's invasive and involves, you know, sticking something up your body. And what I've learned too is that, you know, for most patients, you know, they kind of put you on some kind of anesthesia, maybe not complete anesthesia, but maybe, you know, maybe at least just to dull your senses to make it more pleasant. So you kind of don't really know what's going on. But one thing I've learned after sitting in a few of these rooms, that doctors can have a lot of fun at your expense too. And so, you know, they'll make fun of your appearance and stuff like that, and they'll kind of make jokes about you while you're knocked out. So that's another reason. If you don't want doctors and nurses to make fun of you, then maybe try to avoid having one of these procedures done at any point in your life. All right. Any questions on catheters here? Okay. Another really interesting. So this is kind of a branch off of catheters. So this is kind of a relatively new technology. And so it's called IVUS, which stands for intravascular ultrasound, and OCT, which is optical coherence tomography. These are kind of new imaging modalities that actually make use of the catheter. And so the way these work is that it kind of utilizes some of the same technology in terms of CTs and ultrasounds, but they kind of put that at the end of a catheter. And so, you know, there are some cardiovascular diseases where you either want to view the exact cross-sectional shape of a blood vessel. So this could be situations where, you know, you're kind of concerned about, you know, maybe there's plaque that's kind of, you know, messing up this cross section, and so you maybe only have a small cross section here. Maybe it was difficult to view in the CT scan, and so the doctor may opt to do something like an IVUS or an OCT to kind of get a better view of that cross section area. And so the way it works is that, you know, once the catheter is inside you, you know, they put either an ultrasound device, or they put you know, some kind of CT device, an X-ray device at the end, and then they kind of use that with its own transducer to kind of view an image from literally inside your blood vessel, which is you know, kind of crazy to think about. And so, you know, one thing that you can view from this, you know, again, you know, this gives you really beautiful images of the cross-sectional area. But if you want to view things like one thing that we'll talk about, you know, when we talk about cardiovascular diseases, is that if you have plaque disease, you have plaque that's building up inside your body, you can actually view the thickness of the plaque cap using these technologies. And so, depending on how thick that plaque cap is, you know, you may be in kind of immediate danger of that rupturing. So that's something you may want to take care of immediately. So something like this would be good for viewing that. Yeah. So on the one hand, you know, IVUS uses ultrasound, and then OCT uses infrared light to produce these images. And so mechanically, you know, ultrasound, infrared light, these are different, but kind of the end result is roughly the same. So this is something I've also not been super keeping up with how the technology's been going, but I remember when I was kind of really looking into it back in 2020, it was kind of really exciting. So I'm sure there's been some exciting new developments then as well. All right, any questions on this? Yeah.
What's like the like size of a catheter?
Yeah.
It only functions in like major blood vessels essentially.
Yeah, so they're pretty small, and so I think the diameter of a catheter is on the order of a couple millimeters, just because they have to get into some of these blood vessels. And so, you know, so that also kind of limits kind of where it can actually go, because even the biggest blood vessels in your body only have a diameter of a couple centimeters. And so you'll see catheters mostly used in the heart, because that's those kind of the valves and stuff in your heart are kind of in that size, and maybe in some of the major arteries. But you know, if it's something kind of a smaller vessel in your arm or something like that, then the catheters are not that useful there. Okay. So that's just kind of a very quick primer on medical imaging. There's certainly more out there, and even with everything that we discussed, there's a lot more that we can talk about. But you know, for this class, you know, we're focusing mostly on the application. So let's talk about that a bit more. Okay. So I think the number one application for medical imaging is to view geometry and to view motion inside the person's body, right? And so blood vessels, very similar to your internal organs. These are not things that you can view from the outside of a person's body. But with that said, there are a lot of issues within the cardiovascular system that would warrant either a doctor's attention or an engineer's attention. And so before a doctor can diagnose anything or to give a patient any advice, they have to kind of see what's going on. And so, medical images are used to kind of give doctors kind of that first image or that first view inside a patient of what their condition is, so they can kind of start to plan a treatment from there. Okay. And so some examples of this. So this is probably the primary one that we're going to be dealing with. So cardiovascular plaque, that's called atherosclerosis. This often causes a narrowing of a blood vessel. So this is something that you can see in the medical images, and you can obviously give advice to a patient of hey, you have a lot of plaque inside your body. You need to maybe watch what you eat. You need to exercise more to kind of take care of this. Okay. For older patients, as their heart starts to not function as well, you can use medical images to see how efficient your heart is pumping, how big your ventricles are getting and how much volume they're ejecting in each heartbeat. Okay. Aneurysms. Aneurysm is a very kind of interesting topic. So aneurysms are kind of these unnatural kind of blood sacs that form inside your body. These are very easily detectable in CT scans, and often these are something that you do want to see if you do need to operate on them in case they rupture or do anything like that. Okay. It happens sometimes that babies are born with either malformations or organs or blood vessels that don't kind of form properly, and so imaging is really important in these cases. Kind of catch them early, so that intervention can be done to kind of fix these issues and make sure that the baby kind of grows up nice and healthy. Okay. The cardiac motion can be viewed as well. And so when your heart beats, if there's kind of any irregular motion, if it's kind of twisting or anything like that, then you can view that using medical images as well. Okay, so these are just some examples of kind of the applications of medical imaging. Okay. So another application, this is kind of more in the realm of kind of functional imagery, is to kind of actually measure some things using the imaging. And so the most common application for our case would be to view the blood velocity, right? And so using things like Doppler ultrasound. I also mentioned phase contrast and MRI. So these are kind of techniques that can be used to kind of view the velocity of the blood, right? So these can be used to view backflow through a valve. And so maybe a patient needs a valve replacement. You can use imaging to kind of see that. Okay. You can also use it to measure the forward velocity through a valve to see how effective it is at opening. Okay. And you can also view it to view the waveforms. And so what can happen sometimes is that if you have any irregular heartbeat, that might kind of mess up the flow waveforms at different parts of your body. And so you may want to view that flow waveform to maybe plan a treatment around that. And then I think this is the last one. Yeah, it's the last one. And of course, there's that whole branch of kind of functional imaging that can be used for all different kinds of things. And so here's just a few examples, but there's more out there. So we talked about perfusion testing at the beginning of class today. So that's when a contrast agent is injected, and you kind of view that contrast agent as it perfuses into an organ or into a muscle to see how effective that organ is absorbing blood. Okay. There's a specialized type of MRI called a myocardial architecture scan, where it uses a particular sequence to measure the microcirculation around the heart, right? So that's something that's becoming really interesting nowadays too. There's a lot of research that goes into that. And there's also inflammation testing. And so this is another type of MRI using another sequence where you can view kind of inflammation of tissue to see how inflamed or how injured a particular muscle or particular tissue is. Okay. And of course, there's more and more out there that's available. All right. Any questions on this? Okay. All right. So that's medical images. And so, for Thursday, again, Thursday, we're doing our workshop. I'll be giving everyone a CT scan. And so just remember that, CT scan is a three-dimensional image type. And the way that we're going to view the images is we're going to view it as a stack. And so if you kind of remember that, if you remember anything today, that's going to be the most important thing, because you'll see on Thursday, the first time you work with medical images, it's actually pretty disorienting in terms of, what you're looking at, how to control it, how, which slice that you're at. And so, just having this knowledge of how CT scans are organized is going to help tremendously. It's still going to be pretty disorienting, but this will definitely help a lot. Okay, it's 4:50. Let me do one more thing before we end today. And then I'll see you guys for the workshop on Thursday. Okay. So this is a little bit of a continuation of what we talked about last Thursday. So if you kind of remember from then, we were talking about arterial biomechanics. Okay. And so the idea with arterial biomechanics is that this kind of forms our first connection between fluid mechanics and how that actually affects, biological function inside your body. Okay. So, of course, with blood being a fluid, its behavior and its, and the way it performs, it's very closely related to fluid mechanics, and just how that interacts with kind of the cells and the biology inside your body, how we modeled that, right? And so I think we spent a lot of time last week talking about the Windkessel model. All that's going to be really important for this class. Okay. So the one thing that I wanted to cover today is the link between turbulence and blood flow. It'll get there. It'll get there. Okay. I'll just talk until. So you may have heard of turbulence, from your fluid mechanics class. If you're taking a fluids elective this semester, whether it be, I don't think we're offering aerodynamics, but I think probably some of you are in the CFD class with Dr. Monroe. Turbulence is certainly something that's either come up already or is definitely going to come up. And so turbulence is kind of a very general term that we use in fluid mechanics, and it's basically referring to any kind of chaotic and difficult to predict flow. Right? And it's a very important part. If you're going to make a career out of using fluid mechanics in any way, whether you work in the aerospace sector or you work in the automotive sector, you're designing cars, airplanes, turbulence is something that you should be very familiar with. And it's probably something that you're going to curse in your sleep for the rest of your life if you're working with it to any degree. Because the thing with turbulence is that it's difficult to know about it. It's difficult to kind of predict. And so, the image that's often given with turbulence, or I should say first, let me say the opposite of turbulence is laminar flow. And for usually kind of for introductory fluids classes, that's kind of what we focus on. So laminar flow you know, if you're ever curious kind of where it gets that name, is that laminar kind of refers to lamellae, which are kind of different layers of different things. And so, or sheets, exactly. And so if you look at laminar flow, you know, the flow is very nice and orderly. You may have differences in velocity, but that's okay. But everything kind of flows in kind of sheets like this. Okay. So the Navier-Stokes solution that we went over last time, that was based on laminar flow. So laminar flow is good. And so as difficult as Navier-Stokes is to solve, you know, we do have ways to solve it nowadays, right? So we have computers, we have modeling technology, right? And if you can assume that the flow is laminar, you know, you're usually in pretty good shape. Okay. For turbulent flow, I don't want to say that everything goes out the window because it's not. There are some rules that turbulent flow follows. It's just a lot more complicated. So visually, what it looks like is that it honestly just looks like chaos. And so, you know, you might have some velocity goes like this, some velocity like that, right? It looks like a toddler's kind of scribbled on this, but honestly, that's kind of what it is, right? And so to model turbulent flow, there's it's a topic of hot debate actually. So I don't want to say anything. Not that you guys would care, but you know, the random turbulence researcher who watches my YouTube videos will care and will send me an angry message. That's just the kind of people that they are. So I would just say it's very difficult. Turbulence people are freaking crazy. You go to a turbulence talk and it always ends up in a fight somehow. Yeah. Which is why I'm glad I don't study turbulence. So if you recall from fluid mechanics, the main way, so the question is, you know, how do you know if a flow is turbulent or not? There it is. Okay. So when is a fluid flow turbulent? So the main way that we determine whether a flow is turbulent or not is through the Reynolds number. And so the Reynolds number, RE, has a few different forms, but this is the form that's most useful for blood flow. So we take the density, multiply by U, the velocity, times the diameter, divided by the viscosity. Rho here is the density. U is the mean velocity. Okay. And mu is the viscosity, right? So the Reynolds number, it's a dimensionless number. So if you plug everything in here, all the units are going to cancel out, right? And then depending on the value of the Reynolds number, that's going to tell you whether you have laminar or turbulent flow. Okay. So the threshold for the Reynolds number depends on your application, depends on the geometry of your system. Okay. But for internal tubular flow, which is the form of the Reynolds number that we're putting in there, right? That's why there's the diameter. If the Reynolds number is less than 2300, if your Reynolds number is less than 2300, then your flow is laminar, right? If your Reynolds number is greater than 2300, then we characterize that as turbulent. Okay. And it's not a hard cutoff, and so there's usually a buffer range where we say the flow is often called transitional. And so if your Reynolds number is in the ballpark of like 1800 to 2900, where you're kind of on that borderline, you'll probably see some characteristics of turbulent flow, but maybe not full blown turbulence. So there's a range, but if you wanted to have kind of a cutoff, 2300 is that cutoff. Okay. Okay. So what are the Reynolds numbers like in blood flow? So for blood flow, luckily for us, we're working with very, very small diameter tubes, right? And so the biggest blood vessel, I think, has a diameter of 3 centimeters, which is your aorta. Not only that, the velocities are often very modest as well. And so for blood flow, actually, for the vast majority of the time, you're going to be working with laminar flow. Right? Which is huge, by the way. So it's one of the very few kind of, I would say, kind of more advanced fluid mechanics applications that does not have to deal with turbulence on a regular basis. So it's really, really nice. Okay. And the reason for that is that the diameters. And so if you actually measure the Reynolds number, the maximum that it could ever that it could get is probably on the order of maybe 100 or 200. So it's well short of being turbulence. And so there's really no risk of there. And then as you get into the smaller vessels, that Reynolds number kind of drops to, maybe 10, 2, stuff like that. And so even in the biggest vessels where you're kind of most likely to be turbulent, you still have, mostly laminar. Okay. That said, even though if you're just looking strictly in the blood vessels, you do have laminar flow. There are certain parts of the body where you have kind of turbulent patterns, whereas the flow is not particularly turbulent, but it does show some characteristics of turbulence. Okay. So I call it kind of turbulent-like patterns. And the reason I bring this up is that this is often asked, right? And so, because when you think of laminar flow, you think of flow in kind of a very kind of well-behaved geometry that's kind of following a line. But the thing with the cardiovascular system is that the geometry inside is very irregular. Not only do you have lots of branching paths, but inside the heart you have kind of very irregular flow inside the heart chambers, and also very irregular flow past the valves as well. Okay. And so one example for this is actually flow past a heart valve. Let me give you an example. So let me draw a vessel here. Okay. And so let's say that we're going to look at flow past the valve. And so if you kind of remember, valves are kind of these circular objects with kind of these leaflets. Okay? Right. And so when this valve opens, the leaflets kind of open up like this, right? And so this is kind of a side view here. So the leaflets kind of open up like this, and then flow kind of exits through there, right? And so if you took kind of a cross section of the vessel, right, when the valve opens, right, the leaflets kind of stick in the way of the flow a little bit, okay? Even for the most healthy valves, right? So what I have in thick black right here, these are the valve leaflets. Okay. And then as the leaflets open, of course, blood's going to flow through. And so the blood kind of gets funneled into the middle here. Okay. Right. And then once the blood gets past this leaflet, you kind of have this almost like a little cavity behind here. Okay, so this right here is kind of like a cavity. And it kind of gives a little bit of kind of a suction effect. And so as the flow kind of gets past the valve, you kind of have these kind of, kind of little eddies that kind of form as some of the blood kind of gets sucked into this cavity, especially as the valve kind of opens and kind of closes. It kind of creates that kind of a little bit of a suction. Okay. So these kind of eddies, these are kind of very turbulent like, because that's one of the things of turbulence, that they create these kind of little whirlpools, little eddies. Okay. And so if you were to look at kind of a very detailed simulation of blood flow past these valves, you're going to see them. But even though you see these structures, they're not exactly turbulence. They're mostly just kind of a transient effect due to the geometry of the situation. And so, if you were to move just a little bit further down, you're going to see that these eddies kind of die down almost immediately. These quickly. All right, so there are several kind of locations like this in the cardiovascular system that produce kind of these turbulent-like structures. They kind of look like turbulence, but they're not exact turbulence. And so if you measure the Reynolds number there, it's still going to be very low. And any kind of disturbed flow or kind of circulating flow just kind of very quickly dissipates, and it kind of goes back to being laminar. Okay. So I wanted to mention that just because it's a question that often comes up. And then when we get to the kind of the simulation portion of the class, what you'll see is that we're going to simulate it as if it were a pure laminar flow. It honestly makes it a lot easier to kind of analyze and visualize as well as a laminar flow. Okay. All right. Any questions on this? Okay. All right. So that's all we got time for today. And so we only have 5 more minutes, so we can't really start the next thing. So when we come back on Thursday, if you want to follow along, bring your laptop, so you can follow along with the tutorial. If you just want to kind of just watch, that's fine too. I'm going to post the video for it so you can try it at home at your own pace. But I'm going to bring my laptop on Thursday. We're going to do the tutorial together. And you'll be introduced to Simvascular for the first time. All right, so thank you guys for coming today. I hope you guys enjoyed the lecture today on the medical imaging data. And I will see you guys on Thursday.
We don't have a final on this one, right? No, just cool. With the formula team, we would use like the second week, or no, the week before finals is the competition.
Yeah.
Is there anything we're doing expanding?
So that week is usually I reserve that week for either just project, just working on the project, or just cover something. Just random.
Okay.
Sometimes I have a guest speaker.
So I have to cancel
You guys-
what I would delay.
Cool.
So I did cancel.
Yep.
And that part of it, I was going out, be like, can we go at 3:15? I have a Bible call. No, it's not that way, I got that.